In this video, we're going to learn about the various techniques on how to perform interpolation. This video is purely theoretical and numerical. I invite you to watch a separate video showing how to implement some of the techniques discussed here. Polynomial interpolation consists of determining the unique nth order polynomial that fits n plus 1 data points. This polynomial then provides a formula to compute intermediate values. In other words, you are going to fill in extra data points between two data points. This is in stark contrast with regression, where you instead get the best fit, where the best fit curve does not necessarily and almost always do not pass through the data points. In the interpolation method, your best fit curves always passes through the data points. The simplest form of interpolation is to connect two data points with a straight line. This technique is called linear interpolation. Using similar triangles, we have the first equation. Here we have the two data points, x0 and f of x0, and x1 and f of x1. We want to know what the value of the function is at x. In order to do that, we use similar triangles. So we compare this triangle with this triangle. This triangle gives us f1 of x minus f of x0, which is this one, divided by x minus x0, which is this one. So this equation gives us the slope of this line. Similarly, we have f of x1 minus f of 1x divided by x1 minus x, which again gives us the slope of this line. We know that they are equal. Rearranging the terms and solving for f of 1 of x, we have f of 1 of x equals f of x0 plus f of x1 minus f of x0 over f x1 minus x0 times x minus x0. The idea in this equation is not only to know what the value of f is at this point. The idea is to fill in all the points between x0 and x1. So you get one value of x here. Use this equation to solve for the corresponding value of f of x. Get another value of x here. Use again this equation to get the corresponding value of f of x here, and so on and so forth. Eventually, you have a lot of points here, which essentially connects these two original data points. Let's try to solve this example. Estimate the natural logarithm of 2 using linear interpolation. We have the following given data points. x0 equals 1, x1 equals 4, and x2 equals 6. f of x0 is 0, f of x1 is 1.386294, and f of x2 is 1.791759. If you want to solve the logarithm of 2 here, we can use linear interpolation. Here's the equation for linear interpolation. We only need two data points in order to use this equation. Let's first use these two data points. x0 equals 1 and x2 equals 6. For f of x0 is equal to 0, so we have 0 here. f of x1, or f of x2 in this case, is 1.791759. f of x0 is 0. This is x2 and this is x0, so 6 minus 1. We want to know what the value of f at x equals 2, so we use 2 here. So 2, and x0 is 1. Doing the mathematics, we get 0.3583519. If you plot this in this graph, the result is this red X mark. We can see that it doesn't coincide with the true value of ln of 2. In fact, if we compute for the error, we get 48.3%. If we use instead the smaller interval from x0 equals 1 to x1 equals 4, we get 0 plus 1.386294 minus 0 divided by 4 minus 1 times 2 minus 1. So we have 0.4620981. In this case, this number here is located here. and it still doesn't coincide with the true value of L2. The error here is 33.3%. But what we notice here is that if we let these two intervals come closer and closer towards each other, then the error becomes smaller and smaller, and the value becomes closer and closer to the true value. The next type of Newton's divided difference interpolating polynomial technique is the quadratic interpolation. In this technique, you need three data points, x0, x1, and x2. Then we use this equation, f2 of x equals b0 plus b1 times x minus x0 plus b2 times x minus x0 times x minus x1, where b0, b1, and b2 are the coefficients. A simple procedure can be used to determine the value of the coefficients. If we let x be equal to x0, we can compute for b0. So if x is equal to x0, this is f of x0, this becomes 0, and this becomes 0. And we have b0 is equal to f of x0. The result can be substituted back to the first equation, which can be evaluated at x equals x0 for b1. To find f at x equals x1, this will substitute with x1, this will substitute with x1, and this will substitute with x1, and we end up with this term being equal to 0. So we have here f of x1, and we also have here f of x0. So f of x1 minus f of x0, which we have here, then we have x1 minus x0, which we have here. If we put this as a denominator on the right-hand side, then we get b1. Finally, these two equations can be substituted into the first equation, which can be evaluated at x equals x2, and then solve for b2. I leave it to you as an exercise to solve for the expression of b2. Let's consider the same example, but this time we're going to use quadratic interpolation. So we estimate the natural logarithm of 2 using linear interpolation. We have these three data points. And first, we solve for the following coefficients, b0, b1, and b2. We know that b0 is equal to f of x0, and since f of x0 is equal to 0, b0 is equal to 0. Now b1 is equal to f of x1 minus f of x0, all over x1 minus x0. So 1.386294 minus 0 divided by 4 minus 1. So we have 0.4620981 as b1. For b2, we have f of x2 minus f of x1 all over x2 minus x1 minus f of x1 minus f of x0 minus x1 minus x0 all over x2 minus x0. We have all of these values here, and we substitute that here, and we get as final result for b2 equals 0.05187131. Now we can write the quadratic formula. The quadratic formula is given as f sub 2 of x equals b0 plus b1 x minus x0 plus b2 x minus x0 times x minus x1. And we already know b0, b1, and b2, so we write those down here. So we have the quadratic formula for this curve. This is your new equation developed by using quadratic interpolation. So if you evaluate this equation at x equals 2, we have 0.565844, which corresponds to this magenta x here, and the error is 18.4%. So our results can further be improved by using a quadratic equation. You can see the full quadratic equation here. You can see the interpolation as a result of using the quadratic equation. Here, in this magenta line, you can see clearly that it's the curve, or the magenta line, is quite near the true curve, which is the black line. Now, the preceding analysis can be generalized to fit an nth order polynomial to n plus 1 data points. As was done previously with the linear and quadratic interpolations, data points can be used to evaluate the coefficients b0, b1, b2, up to b sub n. For an nth order polynomial, n plus 1 data points are required. So x0, f of x0, x1, f of x1, up to x sub n, f of x sub n. We use these data points and the following equations to evaluate the coefficients. The bracketed function evaluations are finite divided difference. For example, the first finite divided difference is represented generally as f bracket x of I x of j close bracket equals f of x of I minus f of x of j all over xi minus xj. The second finite divided difference, which represents the two first divided differences, is expressed generally as f bracket x of I x of j x of k close bracket equals f open brackets x of I x of j close bracket minus f open bracket x of j x of k close bracket all over x of I minus x of k. Similarly, the nth finite divided difference is given by f open brackets x of n minus 1 down to x of 1 x naught close bracket, which is equal to f open bracket x of n minus 1 down to x of 1 minus f open bracket x of n minus 2 down to x naught close bracket all over x of n minus x naught. These differences can be used to evaluate the coefficients in Newton's divided difference interpolating polynomial. So this is our general equation for the nth polynomial. Here's a table describing how we can obtain the coefficients b0, b1, b2 up to b sub n. If you compare this equation with this equation, we have b0 is equal to f of x naught, b1 is equal to f of open brackets x1 x naught close brackets, b2 is equal to f x2 x1 x naught, and up to b sub n, which is equal to this. And if we take a look at the table, this is actually b0, this is b1, this is b2, this is b3, and so on and so forth. In order to get b1, we need these four values. To get this one, we need these four values. To get this one, we need these four values. Why do we need to get these two if we already have b0? Well, if you're using a linear interpolation technique, then definitely you don't need these two equations. But if you're using quadratic interpolation, then you need at least this equation, because in order to get b2, you will need to get the difference between these two and the difference between this and this. In order to get b3, you need these two, and to get this, you need these two. Now, the Lagrange interpolating polynomial is simply a reformulation of the Newton polynomial that avoids the computation of divided differences. It can be represented concisely as f sub n of x is equal to the sum from I equals 0 to n of L sub I of x times f of x1. This should be f of xi, where L sub I of x is equal to the product from j equals 0 to n of x minus x sub j divided by x sub I minus x sub j, where j must not be equal to 1. For example, in the linear version where n equals 1, this summation runs from I equals 0 to 1. So we need two terms. We have the term involving f of x naught, which is this term, and another term involving f of x1, which is this term. So for I equals 0, then I equals 0 here, then I equals 0 here. We have I equals 0 here. Since I must not be equal to j, then we don't start with j equals 0. Instead, we start with j equals 1. So that the first term is x minus x1 divided by x naught minus x1. But since the product ends at j equals 1, then we only have this term, which is exactly what is written here. X minus x naught, x minus x1 divided by x naught minus x1. Now for the second term where I equals 1, then this means that I equals 1 here. So this can start from 0. So we have j equals 0, x minus x naught divided by x1 minus x naught, which is what we see here, x minus x naught all over x1 minus x naught. And the next term is for j equals 1, but since we don't want the term j equal to I, we no longer compute for that product. So we are left with this term. So this is the linear version of the Lagrange interpolating polynomial. The second order version is given by this equation. For the second order version, we have n equals 2, which means that we have three terms here involving f of x naught, which is this term, f of x1, which is this term, and f of x2, which is this term. Now let's consider these Lagrange polynomials. The Lagrange polynomials are given by the product from j equals 0 to n of x minus x of j all over xi minus x of j, where j must not be equal to I. So for the first term, where I equals 0, we don't consider j equals 0. Instead, we begin with j equals 1 and then end with j equals 2. So the first term here is x minus x1 and x naught minus x1, which is what you see here. The second term here is x minus x2 all over x naught minus x2, which is what you see here. And then it's multiplied by f of x naught. The second term here is when I equals 1. So if I equals 1, then j must not be equal to 1. So we only consider terms j equals 0 and j equals 2. So the first term is x minus x naught divided by x1 minus x naught, which is what we have here. The second term is x minus x2 divided by x naught minus x1 minus x2, which is what we have here. Then it's multiplied by f of x1. The third term is when I equals 2. So for the Lagrange polynomial, we don't consider j equals 2. Instead, we consider only j equals 0 and j equals 1. So for j equals 0, we have x minus x naught all over x2 minus x naught, which is what we have here. And then j equals 1, we have x minus x1 all over x2 minus x1, which is what we have here, multiplied by f of x2. Okay, so this is how we derive the Lagrange interpolating polynomials. These are the equations that we use in order to determine the values between any given data points. Now let's use Lagrange interpolating polynomial in order to estimate the logarithm of 2. The first order polynomial can be used to obtain the estimate at x equals 2. Now let's solve the same problem and use Lagrange interpolating polynomial to estimate the natural logarithm of 2. Again, we have these given data points. So the first order polynomial can be used to obtain the estimate at x equals 2. Here's our Lagrange interpolating polynomial for n equals 1. We already know what these values are, and we plug the values here. So we have for f of 1 of x equals 0.4620981. If we use the second order polynomial, we have this equation. Plug in these values to this equation, we get 0.5658444. And if we actually graph all the data points between x equals 1 and x equals 6, we have this magenta line here. We can see that the error is 18.4%. And if you compare this with example 2, you'll also see that the estimated interpolated line coincides perfectly with the quadratic interpolation using Newton's divided difference, which we previously studied. That is because, like we've said, Lagrange interpolating polynomial is the same technique but rewritten in another form. In some cases, the previous techniques of interpolation can lead to erroneous result because of round-off error and overshoot. An alternative approach is to apply lower-order polynomials to subsets of data points. Such connecting polynomials are called spline functions. The overshoots particularly occur if there's a sharp slope or change on the value of the function, such as the step function as shown. This is where spline interpolation becomes a better choice. The simplest spline interpolation is the connection between 2 points by a straight line. If you enjoyed connecting the dots when you were a child, then you've already been doing spline interpolation. I just wasn't there to tell you the technique. We begin with linear splines. The first order splines for a group of ordered data points can be defined as a set of linear functions. These equations can be used to evaluate the function at any point between x0 and x sub n by first locating the interval which the point lies. Then the appropriate equation is used to determine the function value within the interval. Let's use linear spline interpolation in this example. Fit the data in the table below with the first order splines, and then evaluate the function at x equals 5. So the first thing that we need to do is to determine the slope of these lines. These lines are your linear interpolating functions. So the slope of this line is determined from these two data points, which are these and these. So we have f at 4.5, which is 1, and then f at 3.0, which is 2.5, divided by 4.5 minus 3, which we solve as negative 0.6. Since we know that the linear interpolation equation is f of 1x equals f of 3 plus m1 times x minus 3, where m1 is equal to negative 0.6, we can readily solve for the lines or for the points between these two data points from x equals 3 to x equals 4.5. Between these two data points, the slope is positive 0.6, and the equation of the line is equal to f at x equals 4.5 plus m2, which is 0.6, times x minus 4.5. So from this equation, we are able to get the points in between these two data points at x equals 4.5 and at x equals 7. Finally, for this line, the slope is negative 1, and the equation is f at 7.0 plus m3 times x minus 7.0. Using this equation, we are then able to derive for the points lying between x equals 7 and x equals 9. In order to answer the question, evaluate the function at x equals 5, we use this equation because x equals 5 lies between 4.5 and 7. So we use this equation, plug in 5 here, and we get f of 2 of x. And we get f of 2 of x, f of 2 at x equals 5. Now, how do we know if this is correct? Well, here's the thing. We don't. The objective here is just to get the line that will show us the relationship of the whole data set so that it can provide some physical meaning. We hope that by doing that, the result should provide some relationship between x and f of x that would help us in analyzing this dataset. The objective in quadratic splines is to derive a second-order polynomial for each interval between the data points. So between this interval, we have this polynomial. In this interval, we have this polynomial. And in this interval, we have this polynomial approximating this curve. The polynomial for each interval can be represented generally as shown in the equations. For n plus 1 data points, there are n intervals and consequently 3n unknown constants to evaluate. Therefore, 3n equations or conditions are required to evaluate the unknown. In this case, you have 1, 2, 3, 4 data points. So you have n plus 1 equals 4 data points. So you have n intervals, so that's 3 intervals. Consequently, 3n unknowns, so you have 9 unknowns. And what are these unknowns? A1, B1, C1, A2, B2, C2, and A3, B3, and C3. So if you have 9 unknowns, then you also need 9 equations or conditions required to evaluate the unknowns. Here are the rules in order to determine the coefficients or the unknowns. First is, the function values of adjacent polynomials must be equal at the interior knots. What are the interior knots? In this example, f of x1 and f of x2 are your interior knots. This can be represented as a sub I minus 1 times xi squared plus b sub I minus 1 times xi plus c sub I minus 1 equals f of xi. The second is a sub I xi squared plus b sub I xi plus c I equals f of xi. This could be the equation for the second interval, and this is the equation for the third interval. For I equals 2 to n minus 1. Because only interior knots are used, each of the two above equations provide n minus 1 conditions for a total of 2n minus 2 conditions. What this means is that this equation at x equals x1 must be equal to f of x1. Similarly, this equation at x equals x1 must be equal to f of x1, which makes sense. If we consider at x equals x2, this equation at x equals x2 must be equal to f of x2, and also this equation at x equals x2 must be equal to f of x2. So we have 1, 2, 3, 4 conditions. So if you have n intervals, this means that you have 2 times 3, or 6 minus 2 conditions. So 6 minus 4, you have 4 conditions, as we've originally shown. The first and last functions must pass through the endpoints. This adds 2 additional equations. Here are the endpoints. This adds 2 additional equations. a1 x1 squared plus b1 x1 plus c1 equals f of x1, and a sub n x sub n plus 1 squared plus b sub n x sub n plus 1 plus c sub n equals f of x sub n plus 1. For a total of 2n minus 2 plus 2 equals 2n conditions. What this means is that this at x naught must be equal to f of x naught, and this at x3 must be equal to f of x3. So now you have 4, which is your 2n minus 2, plus 2 here and here, okay, conditions, which in total becomes 6. Third point that we need to discuss here is that the first derivative at the interior knots must be equal. The first derivative of the quadratic equation is f prime of x equals 2ax plus b. Therefore, the condition can be represented graphically as 2ai minus 1xi plus b sub I minus 1 equals 2ai x sub I plus b sub I. For I equals 2 to n. This provides another n minus 1 conditions for a total of 2n plus n minus 1 equals 3n minus 1. What this means is that if we take the derivative of this and the derivative of this, these two, or their derivatives, should be equal at x equals 1. Again, if you take the derivative of this with respect to x and the derivative of this with respect to x, equate them at x equals 2, we should equate them at x equals 2. So you have 2 additional conditions. So that's a total of 8. Since we need 9, we need 1 more condition. The final condition we get from this assumption. The second derivative is 0 at the first point. Because the second derivative of the quadratic equation is f double prime x equals 2a sub I, this condition can be expressed mathematically as a sub 1 equals 0. The visual interpretation of this condition is that the first 2 points will be connected by a straight line. So this is a very simple condition. What this means basically is that A1 is arbitrary, and with respect to your results, only the first 2 data points will be represented by a straight line. The next 2 data points will be represented by the equations that you will derive. Now let's use the same set of data points and use quadratic splines to evaluate the function at x equals 5. So the first 4 conditions we obtain from these equations. This equation was obtained by using these two at x equals x1. So a1 plus 4.5 squared, this is the interior knot. These are your interior knots. So this is 4.5 squared. This is 4.5. So you have 20.25 and you have 4.5 here. Also, you have 20.25 here for A2. You have 4.5 here for B2. And then at f of 4.5, we have 1. So we have 1 here and 1 here as well. The next two conditions we obtain from this second interior knot at x equals 7. So at x equals 7, this will be 49. This will be 49. We have 49 here and 49 here. This is 7. This is 7. So we have 7 here. And then these are 2.5. So we have 2.5 and 2.5. So now we have 4. Next, we pass the first and last functions through the initial and final values. So here are your end knots. So the first function is a1x squared, which is at x equals 3, plus x equals 3 b1 plus c1 equal to f at 2.5. The next is 9 squared times a3 plus 9 times b3 plus c3 equals 0.5. Now we have 6. The next two conditions we obtain from the derivatives of these interior end knots. So the derivative is 2ax plus b. So for the first knot, x equals 4.5, we have 2 times 4.5, 9 times a1 plus b1 it must be equal to 2 times 4.5 a2 plus b2. At the second knot, 2 times 7 is 14, so 14 a2 plus b2 must be equal to 14 a3 plus b3. And finally, the second derivative of the quadratic equation specifies that a1 is equal to 0. Because we've already determined a1 to be equal to 0, we already need to solve 8 coefficients. b1, c1, a2, b2, c2, and a3, b3, c3. Now, how do we write these down? We can write all of these 9 equations in matrix notation. We already know how to do this because we've learned this from the previous lessons. Now, this is simply a matter of taking the inverse and multiplying the inverse by this column matrix. The solution is then b1 equals negative 1, c1 equals 5.5, a2 equals 0.64, b2 equals negative 6.76, c2 is 18.46, a3 is negative 1.6, b3 is equal to 24.6, and c3 equals 91.3. So now we have these coefficients and we can plug this into our equation. So we have f1 is equal to a1x1 squared plus 8 plus b1x plus c1. But since a1 is equal to 0, we have negative 1 plus 5.5. This is valid between 3 and 4.5. f of 2 is given by this, valid between 4.5 and 7. And f of 3 is given by this, obtained from these coefficients, valid between the values of x equals 0 and x equals 9. To get f of 5, we use f of 2 because x equals 5 is between these two, between this interval or within this interval. So f of 2 of 5 is equal to 0.64 times 5 squared minus 6.76 times 5 plus 18.46, which gives us 0.66. We note that at x equals 3, the value is 2.5, which is expected. Also at x equals 4.5, the value of f of 1 is equal to 1. The value of f of 2 is equal to 1, which is expected. F sub 1 prime of x is equal to negative 1, and f sub 2 prime of x is equal to negative 1.1. This is just a round-off error. X equals 7, f of 2 and f of 3 must be equal to 2.5, okay, which is what we have here. The derivatives are the same. At x equals 9, the endpoint must be equal to 0.5, which is what we have here. If we graph these three equations, plot them against the first order spline, we get this. So the black curve is the first order spline, and the red curve is the quadratic spline. How do we know which is correct? Well, again, we don't. We need to see the full picture, or we need to see the whole data set in order to figure out what the real relationship between x and f of x is. The third type of spline interpolation is when you use cubic splines. Hopefully you already understand how these coefficients were obtained for quadratic splines. We use precisely the same technique in order to obtain these coefficients in cubic splines. Here are the step-by-step method. Of course, there's always a shortcut. And here is the shortcut. The alternate method requires the utilization of the following cubic equation for each interval. You don't need to do anything because this equation has already been derived. This equation contains only two unknowns, the second derivatives of each interval, this one and this one. Okay, you only need this derivative and this derivative. Okay, the rest are known quantities. How do you obtain these second derivatives? You use this equation. So if this equation is written for all interior knots, you have n-1 simultaneous equation resulting with n-1 unknowns. In the example, you have two interior knots. So since n is 3, because this is a cubic spline, then you need two simultaneous equations with two unknowns. So you get 4 equations. So let's use the equation in order to determine the equations for the cubic spline at each interval. So let's consider the first interval. The first interval is between 3 and 4.5. So this is x naught, this is x1. So we have your x1 minus x naught. This is x naught, so f double prime of x naught plus 2. x2 minus x naught, f double prime of x1 plus x2 minus x1, f double prime of x2 is equal to 6 over x2 minus x1 times f of x2 minus f of x1 plus 6 all over x1 minus x naught times f of x naught minus f of x1. In order to get f double prime here, so we use these known values and plug it in here. We get 4.5 minus 3, f double prime of 3, plus 2 times 7 minus 3, f double prime of 4.5, 7 minus 4.5 times f double prime of 7 is equal to 6 over 7 minus 4.5 times 2.5 minus 1 plus 6 over 4.5 minus 3 times 2.5 minus 1. Okay, this gives us 8 times f double prime 4.5 plus 2.5 f double prime 7 equals 9.6. If we use this interval, we get this equation. 2.5 f double prime 4.5 plus 9 f double prime 7 equals negative 9.6. So now we have two equations and two unknowns. If we solve them simultaneously using matrix techniques, we get f double prime at 4.5 equals 1.67909 and f double prime at x equals 7 equals negative 1.53308. Now we substitute these values into this equation. In the first interval, we get this, and the final result is this. In the second interval, we have this result. And in the third interval, we have this result. I invite you to derive these three equations, f of 1, f of 2, and f of 3 of x, in order for you to understand the whole process. To solve for the function at x equals 5, we naturally use the second equation, which covers the value of f at x equals 5. So at x equals 5, we have 1.102886. Looking at the graph, the black line corresponds to the linear interpolation, the red curve corresponds to the quadratic interpolation, and the green curve corresponds to the cubic interpolation. You can see that the cubic interpolation is much smoother, while the quadratic interpolation has these overshoots, which does not really represent the behavior of our data. So here's a summary of all the techniques that we've learned so far for both regression and interpolation. You can see here the error associated with the data, the match of individual data points, the number of points match exactly, programming effort, and some comments that you need to study in order to understand how to implement or which technique to use. I hope that you've learned these basic techniques of polynomial interpolation. These techniques provide a means of approximating a function, especially if you're looking for some sort of trend or mathematical relationship within your data that will help in further analysis. I also hope that you're not that much overwhelmed by the complexity. If you want to understand how things work, you really have to delve in the details and understand the step-by-step process. Get a pen and paper and write down each step. There are 3 or more separate videos explaining how to implement exercises 1, 2, and 3 in MATLAB only. I have provided MATLAB and Python codes that you can study in order to better learn the process. In the machine problem, it is your task to show how to implement in MATLAB or Python the cubic spline interpolation technique. See you in the next video!